right, in this problem, which I took out of former edition of the book, it refers to a pulley. It's really more of a spool. So what you have is the spool has a smaller radius and a larger outer radius. So what you have here is on the outer radius, you have some line wrapped around, and a mass A is connected to that. And off of the inner circle here, mass B is connected. Now, mass A, we're told, is 60 kilograms, mass B is 70. So mass A has less weight, but it has a bigger moment arm. And here you have B with more weight, but less moment arm. So it's not clear which one is going to win that battle. All right. The spool, or pulley, 30 kilograms, and we're given the radius of gyration. So the idea here is that somebody has their hand right up in here and is holding these masses in place, and they kind of move it away, and gravity can take over, and one side or the other will win. All right, so we're told it's going to start from rest when the hand is pulled away. And then after 4 seconds, you're asked what is VA and VB. So we have velocity after a period of time, which is generally a very good clue that you're looking at momentum. So since we have these two are translating, but this one is purely rotating, there's no way that we can express this relative to linear momentum. So as a result, we have to, but the good news is we derived our equations, we noted that things that are translating relative to a point that's rotating, like this point P here, we can express A as linear momentum, as angular momentum relative to P, and likewise B as angular momentum relative to P. And that's great because we can only express this spool as angular momentum. So then we can relate everything. So we're going to use angular momentum. So P here is actually G, the center of mass of the spool. So we'll just note that. IP here is mass times radius of gyration squared. So there's our mass moment of inertia. And we noted stuff is starting from rest. So what matters then is the sum of the external moments about P. That's where we're going to take this about P. And this will be H2 about P. All right, so external moments applied to P. Due to gravity, you'll have 60 times 9.81 times 0.35, the moment arm here. That's trying to drive this counterclockwise, so that's positive. B is clockwise, so negative. So 70 kilograms times 9.81, and its moment arm is 0.275. Applied for 4 seconds, and we get that. Okay, now H1, because there's nothing moving, so there is angular momentum is initially 0. Let's look at H2. So there are 3 masses. We have the 2 that are actually translating, and then the rotating spool. So starting with the spool, all right, it's P here, which is the center of gravity. The velocity there is 0, so this whole term disappears. This is actually from G to G, or P to P, so it's 0 as well. So this term really wiped out. So here we have mass moment of inertia, the center of mass, times omega 2, which we'd like to figure out. All right. Now, for A, since we're taking our angular momentum from this point P, we'll note that omega A has no angular velocity, so omega A is 0, that term goes. Likewise, omega B goes. Those are 0. So we need to go from P to A cross with the velocity of A, and likewise with B. So these are the 2 terms left over. And so what I've done here is, here's IP times omega coming down. And so here, R from P to A, you can see that right here, is minus 0.35. We come back, and then we're going to drop some amount A. I just have plus question mark Y. We don't know how far up or down that is, right? Definitely know it's down, just not how far. Cross, mass, and then I took the velocity to be positive. All right, if this thing's spinning, then the velocity of A will be negative, but we'll let the signs work out for that. That'll tell us everything. Likewise for B, then it's R is 0.275 in the X, not sure what it is in the Y, but then we have a VBY. Y cross Y is 0, so we don't need that distance. And again here, Y cross Y is 0, so how far up or down this would be, it's irrelevant. All right, so VA. If we look at this, we can see this is these are separate variables, so we need to, we want to get down to one variable. So I'm going to express velocity in terms of angular velocity, and that would be omega cross r from P to C. So VA, whatever the velocity is at C, A will have the same velocity. So omega cross r from P to C will give us that. Similarly, omega cross r from P to D will give us the velocity of B. So what I did is I took these, substituted them in, and so here we have for the first one omega z cross minus 0.35x, so on and so forth. So we stuck them in, did the cross products, and when we do that, we get the following from H2, 14.52 omega. And so then we can just equate that to the sum of moments, which is right here. Solve for omega, then multiply by the moment arms, and or the radius associated with velocity, and we get VA, and we get VB. So it pops out quite easily.